So we ended up last lecture was talking about carrier lifetime. Can everyone see her? Should we maybe grab one of the lights? We'll start off today's class, just one of them. Yeah, that might be too much. I think that's sleep-inducing. Can everyone see here? Okay, we'll get started in the meantime. So I think with carrier lifetime, it's very useful to look at this in the terms of in context of a problem. First of all, what is the definition of carrier lifetime?
Generation recombination. Right.
Yes, it's the average time between generation and recombination events. So it's the average time a electron or hole lives before it between when it's generated. So we're talking about these carrier processes up here. The difference in time between the generation of the carrier and the recombination. So a good example problem is just to assume it's a simple problem here. So we have a piece of silicon that we're going to illuminate with light. All right, this example is p-type silicon. And we're going to illuminate the whole thing with light. But it's only going to be a pulse of light. So we're going to turn the light off and turn it off immediately. You can deliver pulses of light with pulsed lasers. Okay, they're only on for they can be as little as femtoseconds. Okay, so it delivers a lot of energy in just a very, very short time period. So if we were to if this is the time on the x-axis, then what we're doing is we are delivering, the laser energy is coming in at t equals 0, and then there's no laser energy after that. So this is the laser energy on the y-axis, and it's time on the x-axis. So we're basically pulsing the light at time equals 0, and then turning the light off. So when this happens, obviously we're going to generate a bunch of electrons in the material, and we're also going to generate a bunch of holes in the material. Remember that electrons and holes are created in pairs, right? So at some point, these electrons and holes are going to recombine and disappear. The p-type material already has electrons and holes in the material. That's because it's doped, right? But when you shine light on the material, you're generating excess carriers. Right, so just to make sure that we're all on the same page with regards to notation, N0 and P0, this is the electron and hole concentration due to doping. All right, that's not drawn in this diagram. That's the amount, the base amount, electron hole concentration that you start off with. And let me just color this so you can see N0 and P0. So this is the electron and hole concentration. I'm going to say the excess. I don't have the right symbols there. We're going to call this sigma n and sigma p. Is the excess electron and hole concentration that's due to the light shining on the material. Okay, and then we also have N and P. This is the total electron and hole concentration. So you can imagine that N the total electron concentration is equal to the initial amount due to doping plus the excess generated by the light, and the total hole concentration is the initial amount plus the excess generated by the light. And what's the relationship between sigma n and sigma p? They should be equal to each other because they're generated in pairs. Right. Good. So, at least initially, sigma n and sigma p are equal to each other. The only situation where they are not equal to each other is if they have different recombination rates. Sometimes electrons can possibly have different recombination rates than the holes do. So getting back to this problem then, so if we are to plot so let's say we plot versus t, we plot, let's say, sigma n. What is this plot going to look like? So we apply a flash of light at time equals 0. Yes, that's right. The first point is like the excess electron concentration is going to spike up at time equals 0. So it'll go up like this. But then we immediately turn the light off. So what's going to happen after that? Yes, exactly. Exponential decay. You're both right. Raphael, you're correct too. It takes some time for it to decay. And the relationship, the function that it follows is an exponential decay function. So it looks something like this. This is what we ended off in class with last time, but we're doing a specific example of it this time. All right, this function is described as so sigma n of t equals sigma n0 e to the negative t over tau. And tau is the carrier lifetime. We ended up class talking about this example here. This is the same function that I graphed at the end of class last time. A large tau means that you have a gradual decay. So that's the green line here. And a small tau means a rapid decay. So the tau in an exponential decay equation is described as a rate constant. And that term rate constant you've probably, or you may have heard before in your differential equations class, in other engineering classes, because we see these exponential decay functions a lot in nature. So if we were to take this and then plot it, if we were to take the same function and plot it versus time, except we plot this on a log scale. So this is log sigma n of t. Then this will actually look like a straight line. The reason why is if you take the log of an exponential function, so if we were to take log of sigma n0 e to the negative t over tau, we can end up with log of sigma n0 times log of e to the negative t over tau. And what happens when you take the log of an exponential function? They cancel each other out. So let's be more specific. Let's call this ln, natural log. So if you take the natural log of an exponential function, you'll end up seeing just whatever's in here will be left. So negative t over tau. this part here is just a constant.
So you just
Okay, so it becomes a linear function, right? So this is what you're seeing on this graph here. So in this example problem, so we had p-type gallium arsenide with Ni equals 10 to the 6th. It's doped with P equals 10 to the 15th acceptors per centimeter cubed. So the concentration of electrons, so the concentration of holes is 10 to the 15th because that's the doping density. The concentration of electrons we can figure out by Np equals Ni squared. You can find that as 10 to the negative 3. And then we have a pulse that creates 10 to the 14th electron hole pairs per centimeter cubed at time equals 0. And the question is, what is the electron and hole concentration versus time? The solution of it is shown right here in this graph. So I mentioned this is a log scale, so you end up seeing a linear line representing that at the exponential decay function. So this is plotting the total carrier concentration. So just to be clear, this is plotting N and P. It's not plotting N0, P0. It's not plotting sigma N, sigma P. It's plotting N and P, so the total electron and hole concentration. So just to be clear here, in this case, in this example problem, N0, P0 is 10 to the 15th. N0 is, we calculated already, 10 to the negative 3 per centimeter cubed. Sorry? It's 10 to the minus 3. Sorry, this is not. There we go. 10 to the minus 3 per centimeter cubed. And this problem is saying the pulse creates 10 to the 14th electron hole pairs per centimeter cubed at t equals 0. So the 10 to the 14th is this sigma n0. Okay, it's telling you that the laser pulse created 10 to the 14th excess electrons and holes at time equals 0. So sigma n0 is equal to 10 to the 14th. All right, and since they're created in pairs, sigma p0 is equal to sigma n0, and that's 10 to the 14th per centimeter cubed. So all you need at this point to figure out what the decay function is just the time constant. So if in a typical problem, I'd give you the carrier lifetime. I'd give you tau. So then you could generate a plot of the excess carrier concentration versus time, and you could tell me what the carrier concentration is at any given time point. All right, so that's what this problem is showing. Now, the graph, like I said, is showing the total electron and hole concentration. So what I want to point out here is that notice that this is, the hole concentration here is 10 to the 15th. The electron concentration is 10 to the negative 3. So the total hole concentration, P, is going to be equal to P0 plus sigma P, and N is going to be equal to N0 plus sigma N. Now this is going to change. This is a function of time. This is also a function of time. So P0 plus sigma P0 e to the negative t over tau. So let's just plug in the numbers here. 10 to the 15th, and this is 10 to the 14th. And we have 10 to the negative 3 plus 10 to the 14th e to the negative t over tau. All right, so what we notice about the hole versus the electron concentration, what can you notice just by looking at these equations here? What's different about the electron and hole concentrations? They're definitely out of balance, yes. More specifically, there's many more holes. If we look specifically at this equation, we notice that this is 10 to the 15th, and this is 10 to the 14th. So these are similar in magnitude, right? They're about a factor of 10 off. Now this e to the negative tau function, remember this part here, this ranges from 1 to 0. Okay, when time is equal to 0, this part is going to have a value of 1. And then as time increases, it's just going to decay to 0. All right, so the maximum value that this part of the equation can have is 10 to the 14th. So these are then comparable to one another. Well, this is an order of magnitude less than this. So the total amount is going to be 10 to the 15th plus 10 to the 14th e to the negative t over tau. The maximum number of carriers that you're going to have at time equals 0 is just 10 to the 15th plus 10 to the 14th. So if I were to ask you, what is the carrier concentration at t equals 0, the total carrier concentration, you could say it's just 10 to the 15th plus 10 to the 14th. This t here is 0. In the case of the electrons, you know, if I asked you the same question, you'd say that it's 10 to the negative 3 plus 10 to the 14th. This electron concentration is much, much less than this excess amount. Right, so the initial amount, in the case of holes, the initial amount is greater than the excess amount. And in the case of electrons, the initial amount, due to doping, is much, much less than the excess amount generated by the light. Okay, this type of situation is referred to as low-level injection. And let me explain a little bit what more this means. We have a p-type semiconductor here. So this is called the majority carrier. In a p-type semiconductor, holes is the majority carrier. In an n-type semiconductor, electrons are the majority carrier. So in this case, holes are the majority carrier and electrons are the minority carrier. All right, so in the case of low-level injection, let me write this down. Low-level injection. The definition of that means that the majority carrier concentration changes only slightly. So let's say it changes by less than 10%. But the minority carrier concentration, let's say that can change significantly. The minority carrier concentration can change significantly. So this is the definition of low-level injection. High-level injection will be when the majority carrier concentration changes by more than 10%. Let me just write that down just for clarity. High-level injection is when the majority carrier concentration changes by more than 10%. So this particular example is an example of low-level injection, because you can see that the majority carrier concentration has not changed very much. It changes at most by 10% at time equals 0. But the minority carrier concentration has changed quite dramatically. It's gone from 10 to the negative 3 without the light, 10 to the 14th with the light present. So that's what's being shown in this graph here. This is showing the total hole concentration up here and the total electron concentration down here. So the total electron concentration is approximately 10 to the 14th at time equals 0, because at time equals 0, this is essentially insignificant compared to this term here. So your total electron concentration is really going to be determined by this portion of the equation. And for the majority carriers, this is the significant term. So you can see for the majority carriers, it looks more or less like a flat line. For the minority carriers, it looks like an exponential decay. These are all the excess carriers that were generated. The excess carriers changes the electron concentration very significantly, but it doesn't change the majority carrier concentration as much, at least from a percentage standpoint. Does that make sense? So the fractional change in the majority carrier concentration is small. Okay, so you will have an example problem like that in the homework. So moving on now. First of all, any questions about this that I can help clarify? How do I derive that percentage? Good question. Let me plug this in. All right, so let me make up a question here. Let's say I ask.
Just the 10 to the 15 plus 10 to the 14. That just seems like a pretty significant increase.
So let's say at t equals 0. What is the percentage change in hole and electron concentration? So the percentage change for holes, percentage change will be equal to the delta P, the change in hole concentration, divided by the original amount. So the change in hole concentration is just the sigma P, and this is the original amount. So it would be 10 to the 14th. So this is sigma P at time equals 0. 10 to the 14th divided by 10 to the 15th. So this is about 10%, 0.1. So for electrons, let's call this P, holes, and then electrons, percentage change is equal to the change in electron concentration divided by the initial amount. So it's sigma n0 divided by n0, and this is now 10 to the 14th divided by 10 to the negative 3. So this would be a lot. 10 to the 17th, 10 to the 17th. So that would actually be 10 to the power of 19%. right? Because if you want to change a number to percentage, you multiply by 100. So I do want to make one point of distinction here. The absolute number of electrons and holes that were created are the same, because sigma n is equal to sigma p, right? When we're talking about the percentage change, the change from the original number to the new number, the amount that was changed, so these percentage changes that I just calculated, there's a very big difference here. All right, the majority carrier concentration changed by 10%, which is not that much, but the whole concentration changed by a very large fraction. Does that answer your question?
Yeah, it was just looked funny. It was 14, 15. Seemed like a much larger proportion.
Oh, okay. So I'm glad we went over this anyway, because there's a problem in the homework which asks you to calculate the percentage changes. Yes?
You mentioned the recombination rate could change the quality of the excess carriers and holes?
Yes.
Is that right?
Yes.
So I just understand that anytime you create an electron, you create a hole. So even if they recombine at a different rate, you're still losing equal amounts. So
Oh, yeah, that's.
So I don't understand where you can get more electrons and holes, even if they're combining at any different rate.
Yeah, that's a good point. I know that it is possible for them to have different recombination rates.
Sure. Okay.
Because the electrons and holes behave differently in the crystal.
Okay.
So the probability of them colliding with another, the probability of an electron colliding may be different in some crystals than the probability of a hole colliding.
So
I mean, in general, in this class, for most of the things we're going to be looking at, the recombination rates are the same.
Okay.
But in different, more complex systems, I see your point here. Like if an electron recombines, so does a hole.
Okay.
But I think there's a more, yeah.
Fair enough.
Yeah.
But you can lose the electron from the material. Like the electron can still lose an electron without lose a hole for the recombine. No, don't you?
Say that again.
Are there any way to the electron escape from the structure without combining the hole?
Is it possible for an electron to escape from the structure?
Yes.
It is possible for an electron to escape from a lattice, but that's a different concept. That's something called the photoelectric effect. If you shoot a beam, a high energy beam at a material, you can actually remove the electrons completely. That's called ionization. That's something we'll talk about in one of the future chapters. Good question. Okay. So moving on then, let's talk about another problem. What is equilibrium and what is steady state? So the example problem that we just did was an example of a non-steady state problem, the example of a transient problem. Let's think back to circuits. Okay, when we do a transient analysis, remember in circuits, how many of you have taken circuits 2? Okay, all of you have taken circuits 2. Do you remember in circuits 2 where you did transient analysis? You closed the switch, and then you said, okay, find the voltage as a function of time. And you remember how we saw that, if you're looking at the voltage of a capacitor versus voltage over a capacitor versus time, often you saw exponential relationships, exponential decays. Okay, we see similar things when we're just looking at the number of carriers in a semiconductor. But the point I'm trying to make here is that that's an example of a transient problem. This is where you analyze something with respect to time. And the way that you've stimulated the system is by a transient change in the system. For example, you closed a switch, you opened a switch. That causes a transient change in the system. That's an example of transient, non-equilibrium, non-steady state analysis. That's the most general case. Okay. With circuits, then you also did steady state analysis. Right? Steady state analysis is where you're finding the DC voltage and the DC current. Those are the easiest types of problems. And then there was also an equilibrium problem, which was so easy you probably don't remember it at all. An equilibrium problem is when there is no stimulation to the system at all, meaning no voltage is applied, no current is applied. All right. The reason I'm rehashing those concepts now is just so you understand how the equilibrium, steady state, and transient analysis applies to semiconductors. With semiconductors, we can also apply some sort of stimulus. In this case, we're doing a lot of optical stimulus. In this module, we're talking about optical stimulus. We're shining light at the material, which generates electron-hole pairs. So in the case of transient analysis, it's a flash of light. We turn the light on and we turn the light off. And we look at how the carrier concentrations change with time. As we saw in the example transient problem, we know that the carrier concentrations, and we'll talk about diffusion currents as well, diffusion currents can change with time. So it's a function of t. We're now going to talk about the steady state situation where we have a stimulus, but it's constant in time. So we're going to turn the light source on, and that's going to generate electrons and holes. Those electron and holes are going to recombine, but since we have a constant amount of light coming into the system, we're going to generate more electrons and holes. Right? So there's going to be generation and recombination happening. We're going to establish a steady state electron and hole concentration. That's the second type of problem. So external excitation can be applied in a steady state problem. In the case of circuits, you applied a voltage or current source. In this module, we're applying a constant light source. All processes are constant and balanced by opposing processes. When we turn on the light in the semiconductor, we generate electrons and holes, but they also recombine. And the two processes come to balance at steady state. In steady state, there can be currents, but the spatial carrier concentrations do not change with time. Okay, the spatial concentrations, you have spatial carrier concentrations, but they do not change with time. Then the simplest situation is where we have equilibrium. Equilibrium is what we did last chapter. We just dope the material, but we don't apply any stimulus to it at all. We figured out the electron and hole concentration. Those are very simple problems to do. No external excitation, no light, mechanical, or electrical fields. You're at constant temperature. And in those cases, you don't get any net current, and the carrier concentrations do not change with time. You can just figure out N0 and P0. That's it. So if I could maybe add one thing to the slide here. Try this. So in this, oh, no, I want the pen. There we go. So in this type of problem, we have N0 and P0. That's what we did last module. In this type of problem, we have N0, P0. We also have sigma N and sigma P. In this problem, we have N0, P0. This is the problem we just did, by the way. We also have sigma N of T, function of time. I don't know why it keeps on doing this. It doesn't like me. And also sigma P as a function of time. All right, so that's the differences in these types of problems. Any questions so far? Let's go to the example here. So what we're doing is we have a semiconductor material. Similar to what I showed you earlier, we're applying light to the material. The difference here is this. Now we're talking about a steady state situation. So we just have light being applied to the material like this. So this is generating electrons and holes. Those electrons and holes are recombining, but the fact that the light is still on is generating more electrons and holes. So the two processes go in balance. Right, so steady state, the steady state carrier concentration is given by this formula here. sigma n is equal to tau n times GOP. Sigma p is equal to tau p times GOP. So what are these things? This is sigma n is the excess electron concentration. Notice that this is no longer a function of time. It's the carrier lifetime, the electron lifetime, tau n, multiplied by GOP. GOP is the rate of excess carrier generation. It's given in electron hole pairs per centimeter cubed per second. So let's put that down here. So we're talking about steady state generation. Sigma n is equal to tau n times GOP. The units for tau n is given in seconds. And the units for GOP is given by electron hole pairs per centimeter cubed per second. So centimeter cubed second is on the denominator here. Just make this S. So when we multiply these two terms together, seconds and seconds here cancels out. So this then becomes electron hole pairs per centimeter cubed, but we often just say 1 over centimeter cubed. We don't say electron hole pairs. Okay. So sigma n would be given in terms of 1 over centimeter cubed would be the units. So the carrier lifetime will be given to you, and this GOP will also be given to you. GOP, it means the generation, the carrier generation rate. The number of electron hole pairs created in a cubic centimeter of material per second. The stronger the light source is, the larger the GOP is going to be. The carrier lifetime is depends on the material, and it depends on the concentration, the electron hole concentration in the material. Okay, as we talked about before, the higher the electron and hole concentration, the smaller the carrier lifetime. Right, and the same is the case for tau p and GOP. Notice that the holes can have a different carrier lifetime in some materials. So the intuition behind this, I mentioned this already. GOP describes the number of carriers created per second. The carrier time constant tau is the mean time each carrier spends in its band before capture. So it's the mean time between generation and recombination events. The multiple of the two gives a steady state concentration in electron hole pairs per centimeter cubed. You can even take out this electron hole pair part of it, just 1 over centimeter cubed. If we just look at this equation, if we want to make sigma n higher, we can increase the intensity of the light, so increase GOP. Or if we're in a material where the carrier lifetime is longer, so when the carriers are being generated, they live longer before they recombine, that will also increase the steady state electron concentration. Right, so this equation is simple, and the intuition behind it should be very clear to you in your heads. So we'll do another example here, and I would like for all of us to try this. We could take our break a little bit early today. So for those of you who want to go out and grab and just stretch a little bit if you're done early, and in the meantime you can also work on this problem. So let's do this. Let's take for about 10 minutes or so. See if you can figure out the different parts of this problem. And if you're finished, you can go take a water or bathroom break. And if you need help, just raise your hand and I'll come by and help you. So here's the problem. Assume we are shining a laser light on an N-type silicon wafer so that in the irradiated area, 10 to the 13th electron hole pairs per centimeter cubed are created every microsecond. So this is your GOP. And one thing I want you to notice is this GOP is given to you in units of microseconds. Okay. Assume the silicon doping is NO equals 10 to the 14th per centimeter cubed, and then your carrier lifetimes are both 2 microseconds apiece. There are several parts to this problem, and you'll have a problem like this in your homework too. If you do it now, it'll really save you time on the homework. And you'll also know what if there's any parts of it that you might be having trouble with. The first part is calculate the equilibrium concentrations of holes and electrons. So here you're being asked to calculate N0 and P0. This is the electron and hole concentration just due to doping. No light on the material. The second part is asking you to calculate sigma n and sigma p. Calculate the excess hole and electron concentration created through irradiation. So when you shine light on the material, you're generating excess electrons and holes. How much is that? The third part is asking you to calculate the total concentration of electrons and holes during radiation. So it's asking you to calculate N and P. And then the last part is what is the percentage change in the number of holes and the number of electrons in the irradiated state versus the non-irradiated state. So it's very similar to the problem that we did earlier. It's actually a simpler version of that problem. So go ahead, we'll take a 10-minute break here, and you can work on this problem and take a break if you'd like. Let's see, discard. So I'm just going to pause this. So this is an example of steady-state generation recombination. I gave you the problem earlier. This next slide shows how to solve this problem. So the first thing we do is before irradiation, we have to figure out the base electron and hole concentration. This is the same problem that you've done in the previous chapter. Just find the electron and hole concentration. So N0 is equal to 10 to the 14th because it's N-type and the doping density was 10 to the 14th per centimeter cubed. I don't have the units here. I should have the units. P0 is equal to Ni squared over N0. All right, and we have the value for silicon here. So it's 2.25 times 10 to the 6th per centimeter cubed. That's the N0 and P0. After irradiation, the number of excess carriers, sigma n, is equal to tau n times GOP. And that's equal to 10 to the, what's going on here? Yeah, 10 to the 13th is the GOP, the generation rate. And 2 times 10 to the negative 6 is the, right, the carrier lifetime. All right. So this units is given in seconds, and the 10 to the negative 6 that we have here in the denominator is to convert this into seconds. Because what was given to you, you're given the generation rate is 10 to the 13th electron hole pairs per centimeter cubed per microsecond. So we have to convert that microsecond over to seconds. They do. I'm putting the 10 to the negative 6 here and the 10 to the negative 6 here just to be absolutely clear. You could just multiply these two numbers together. 2 times 10 to the 13th. You get the same thing. So the sigma n is 2 times 10 to the 13th per centimeter cubed. Since the carrier lifetimes are identical in this problem, tau n is equal to tau p, these two are also going to be equal to each other. So it's sigma p is equal to 2 times 10 to the 13th. The total number of carriers, n is equal to n0 plus sigma n. So it's 10 to the 14th plus 2 times 10 to the 13th. So it's 1.2 times 10 to the 14th per centimeter cubed. The hole concentration is P0 plus sigma p. This is approximately equal to sigma p. Okay, let's see why. The original hole concentration was 2.25 times 10 to the 6th. That's before irradiation. when we shine light on the material, the excess carrier concentration, number of holes generated in the material, is 2 times 10 to the 13th. There's a 7 order of magnitude difference here between these two numbers. So that's why P0 plus sigma P is approximately equal to sigma P, 2 times 10 to the 13th per centimeter cubed. The percentage change, the number of electrons increased by 20%. The way that we find this is just the same way that I showed you earlier. It's the sigma P or sigma N divided by N0. The way that you find the whole increase is sigma P divided by P0. So the electrons increased by 20%, the number of holes increased by 10 to the 9th percent. All right, so this would be bordering, this would be low-level injection, but it's sort of bordering on high-level injection. Any questions about how to do this problem? Okay. It's a pretty straightforward problem. So adding to this problem, when we do Quasi Fermi levels, Quasi Fermi levels are, it's a way of representing these excess carriers in an energy band diagram. So when we generate carriers in a material, the hole and electron concentrations will change. And one way that we can represent this is by using Quasi Fermi levels. So this Quasi Fermi level only applies to steady state analysis when we have some type of optical excitation. These are the equations for the Quasi Fermi level. N is equal to Ni, e to the Fn minus Ei divided by Kt. P is equal to Ni, e to the Ei minus Fp divided by Kt. And what it will look like is something like this. Say we have an example problem here. From the previous example, draw the energy band diagram showing the original Fermi level before irradiation and the new quasi-Fermi levels Fn and Fp after irradiation. So we can sort of go through the general idea here. You'll have a problem like this in your homework. Quasi-Fermi level. So we can draw two diagrams for, well, let's just draw both on the same one. Let's start off with the band diagram before irradiation. So we have EC, EV. We can draw in here EI. And we can put the location of the original Fermi level. So back up to this question here. So the electron concentration was 10 to the 14th. This was an N-type semiconductor. So the Fermi level will appear somewhere up here, but we want to figure out the exact location. And do EF minus EI equals KT ln of ND over Ni, 0.026 times the natural log of 10 to the 15th. Was it 10 to the 15th? Yeah. Oh, sorry, 10 to the 14th. Divided by 1.5 times 10 to the power of 10. And this comes out to, can someone help me here?
0.23?
Okay, thank you. 0.23 electron volts. All right, I know this will be about halfway because I know this distance here is about Eg over 2, so this is 0.56. And so this should be about 0.23 electron volts. So this is our EF. Now if we want to find the Quasi Fermi levels, we can use these equations. N is equal to Ni e to the Fn minus Ei divided by kT. So when we solve for Fn minus Ei, we're going to have something like this. Fn minus Ei equals kT ln of n over Ni. All right, notice the difference. When we're finding the quasi-Fermi levels, instead of just putting the doping density, we put in the total electron concentration. So that's after irradiating the material with light. All right, so this is 0.026 ln of what was it? 1.2 times 10 to the 14th over 1.5 times 10 to the 10.
0.233.
0.233. Thank you. All right. This is 0.233. So what will happen is this. Let me draw this in different colors. So this is Fn. Fn will basically be almost right on top of EF. Now what that tells us is that the electron concentration has not changed significantly. It hasn't changed by several orders of magnitude. So Fn just represents, it's a visual representation of the electron concentration in the material. Then Fp, we can calculate Fp. So Fp, sorry, the formula is Ei minus Fp equals kT ln of P divided by Ni. 0.026 ln. We look at our hole concentration that we found in the previous problem. The total hole concentration, P, is about 2 times 10 to the 13th. Divided by 1.5 times 10 to the power of 10.
0.187.
Thank you. 0.187 electron volts. .233 electron volts. That was the previous part. So if I put in, my FP here, this is telling us that EI minus FP is 0.187 electron volts. So it's going to be somewhere in this region here. This is FP. .187 eV. Right, this FP is showing us that it's showing us the hole concentration, visual representation. What this diagram suggests is that the hole concentration changed a great deal. The hole concentration is below EI, so there's a larger number of holes than the intrinsic hole concentration, which is 1.5 times 10 to the 10. The many electrons are also present, but not much compared to what there was initially. EF represents the electron and hole concentration after doping, but before irradiation from light. All right, so this is just adding to your toolkit of different things to add to your energy band diagrams. All right, right now it may seem like this is just work to make these energy band diagrams, but these band diagrams actually turn out to be very useful for designers who are designing different types of solid-state electronic devices to understand them and to be able to communicate some of the operational principles of devices to other solid-state device engineers. Okay, so that's an example of the Quasi Fermi levels. Let's talk a little bit about photoconductors right now. I think it's always helpful to kind of talk a little bit about applications of some of these types of devices. So we've talked a lot about how semiconductors respond to light. We know that carriers are generated. Now from last module, make the connection here. What do you think is going to happen to the conductivity of the material when we shine light on the material? The conductivity will increase, right? We have more carriers. Conductivity is proportional to carrier concentration and mobility. Right? The mobility, when we shine light on the material, the mobility is staying approximately the same, but we're increasing the carrier concentration. So the conductivity of the material will increase. So it turns out that this on its own is a very useful application. So a lot of sensors are based on a resistance change. So for those of you who have worked with sensors before, have you heard about RTDs, resistance temperature devices? It's basically a resistor that the resistance changes as a function of temperature. Right? So that's used. That's a way to measure temperature. Semiconductors can be used in RTDs, but they can also be used as optical sensors too. When you shine light on the semiconductor material, the resistance changes. And using a circuit, you can detect what the resistance changes. Does anyone know what type of circuit is used to detect resistance changes? You don't need to know it for this class, but just close. It's not quite a voltage divider, but it's close. There's the bridge. That's correct. Have any of you heard of Wheatstone bridges? Wheatstone bridge? A Wheatstone bridge is a circuit that's used to detect changes in resistance. All right, just for trivia's sake, you don't need to know this for this class, but this is a Wheatstone bridge circuit. This is connected to a battery, and this is the output voltage. So this will be let's say this is the resistor in question. When this resistance changes, it changes the output voltage. That's a good way to measure changes in resistance. So photoconductors are light sensors. The conductivity of the light sensor, the conductivity of the semiconductor, when it's exposed to light, it changes to this. Remember that the original formula conductivity formula, sigma is equal to Q times mu n times n plus Q times mu p times p. So this would be for no light. And if we add light into the material, we have more carriers. So it's going to be Q mu n n0 plus sigma n plus Q mu p p0 plus sigma p. All right, so we've added extra carriers to the system, so the conductivity will change accordingly. right? So this is the formula for that. So you can figure that out pretty easily. The more light you put in the material, the more conductive it becomes. There's a few applications of photoconductors. Probably many of you have something like this in your room or in your hallways at home, night lights. So this there's a circuit, a simple circuit in here which detects the resistance change. There's a semiconductor in there. The resistance changes when the room is dark versus when it's light, and that triggers whether the light is turned on or not. Another very common type of application is in exposure meters in cameras. How many of you do photography? How many of you have a digital camera where you have you adjust manual settings on it? Okay, so you guys have worked with exposure times and shutter times. When you have a low light condition, you would like to keep the shutter open for longer periods of time to let more light into the system, to let more light into your camera. So there has to be, when you're in automatic mode, the camera is doing all the calculations for you. It's detecting how much light is in the room, and accordingly it adjusts the exposure time, and it adjusts the aperture, which is the hole in the shutter in the camera. When it opens, it lets in a certain amount of light. So the size of the hole and how long the hole is open is determined by how much light is in the room. So cameras have these light sensors, and they're used as exposure meters. Then there's the old laser-based security systems, where you have a light bouncing off some type of object. These things aren't really used that much anymore, but they're, as I've said in our previous classes, it's great for movies. For those of you who've seen Ocean's 11, there's a scene where the bank vault has all these crisscrossed lasers going across it, those green lasers, and that guy has to, in order to get to the vault, he has to make sure that he somehow gets to the vault without letting his body cross any of the laser beams. It was a really cool scene. I thought that was awesome. But anyway, the way that these types of laser systems would work is that you'd have a laser source here, and that laser source would be emitting a beam of light. And on the other end, you'd have a photoconductor. And this photoconductor would be connected to a bridge circuit. So it's connected to a circuit which detects the changes in resistance. So you have the laser beam coming in here, and it's giving a fixed amount of light to the photoconductor. So there's a certain resistance of the photoconductor. If someone were to come and stand in the way, this would block the laser light, right? And so what will that do to the photoconductor? How will that change the resistance? It'll increase the resistance. That's correct. It'll increase the resistance because with light, you've increased the conductivity. When you take the light away, you've decreased the conductivity, increased the resistance. And so if your circuit can detect that change in resistance, then you have a way of basically of detecting if that beam has been breached. Nowadays, they have better systems. They have infrared cameras and other types of motion detecting devices. So these are just a few applications. One of the biggest applications of semiconductors is in various types of light sensors. The first day of class we talked about the actual CCD chips in cameras. So there's exposure meters here, but then there's the actual light sensor too. It's a computer chip that detects light patterns coming in, and that's what gives you your digital images. The fact is that semiconductors are light sensitive. In silicon, as we learned earlier in this module, silicon happens to be sensitive to visible light. So that's great because then it works very well as a digital camera.
Isn't that by nature silicon is before the semiconductor?
That's a good question. The comment was, is that the reason why silicon was a semiconductor of choice? I think one of the reasons why silicon was initially used is because it's a very abundant material. Sand is silica. You can do some processing on sand to turn it into silicon. And it was a material that the fabrication processes were,
Do they know that that property was with silicon or not?
Yes.
So
Yeah, I mean, the fact that silicon responds to light, generates carriers, has been known for a very long time. Yeah. Yeah, I guess it just so happened that the same material that's used in the semiconductor industry also happens to work very well as a light sensor. So that's one of the reasons why silicon, I guess you could say that's another reason why silicon has become a very popular material of choice.
Is there another material that acts like that?
That can absorb visible light?
Visible light.
Yeah, in fact, any material with band gaps similar to silicon will be able to absorb light. So we were talking about, remember this graph here?
Yeah.
So materials with band gaps similar to silicon, gallium arsenide, you have germanium here. Right. All right. So moving on then. We'll start talking about carrier diffusion, and we'll probably finish up on Thursday. This was a video of chemical diffusion. I don't know. Let's see if it works or not. Could not be found. Okay. Well, chemical diffusion you've all seen, so even if we don't have the video, no problem. Chemical molecules migrate from regions of high concentration to low concentration. So let me just describe to you what the video was showing. You have a beaker full of water, right? You put a drop of food coloring in there. What happens? It disperses, yeah. Initially, the chemical concentration is high where the drop happened, and eventually that drop spreads out, disperses into the rest of the beaker. And after a few minutes, the concentration of the food dye in the water is relatively equal. Right. So that is a nice illustration of chemical diffusion. In semiconductors, the same thing happens. If you were to somehow create excess electrons and holes in one region of the semiconductor, for example, if you were to shine light on one part of a semiconductor material and not the other part, you'd be generating a lot of carriers in the illuminated region, and those carriers would then diffuse over into the dark regions. So that's what we're going to talk about here. So in semiconductors, diffusion will occur if there is a gradient of carriers. If there's a high electron concentration on one side, lower electron concentration on the other. The way that we can do that is by irradiating the sample with light. The speed of diffusion is proportional to the concentration gradient. If you have a very high concentration of electrons here and a very low concentration on the other side, that's the speed in which the carriers diffuse is going to be higher than if the two concentrations are very close together. So here's a qualitative example of carrier diffusion. So you shine light on part of the material. So in that part, just the part where you shine the light, you generate carriers just in that region. Okay, so we had like a collimated laser beam. We shine that through a silicon sample, and we generate carriers just in that region. So this is T1. We generated a bunch of carriers. So as we wait, if we wait some amount of time, then over time these carriers are going to diffuse from high concentration to lower concentration, so they'll diffuse outwards. So after some time it'll look like this. They started spreading out. Sometime later it'll look like this. They spread out even more. And you get the idea here. Now keep in mind that these carriers are also going to recombine. You generated carriers, they start diffusing, and they also recombine. So eventually these excess carriers are going to disappear completely. So the two processes we're talking about here, out of the four processes that we were discussing at the beginning of the module. In this example, we generated carriers using light, while the carriers existed, they diffused because there was a concentration gradient. They didn't drift. There was no electric field, so this effect didn't happen. And then they recombined eventually. These are the equations governing carrier diffusion. So the diffusion rate is proportional to the concentration gradient, similar to Fick's law. In fact, this is a version of Fick's law. Some of you, if you've, are there any chemical engineers in here? No? Okay, usually not. I would expect not. But in chemistry or chemical engineering, you learn about Fick's law. It's just an equation describing diffusion. So let's look at the different parts of this equation. Jn diffusion is, this is the current density. We talked about current density with respect to drift currents in the previous module. This is the the current density with respect to diffusion currents. Jn diffusion is equal to Q. Q is 1.6 times 10 to the negative 19 coulombs times D. This is the diffusion coefficient. And this is dn dx. Now, n of x is the carrier concentration with respect to space. dn dx is the concentration gradient. So for example, the example that we always like to show, just because it's the most intuitive, looks something like this. Let's say we have a piece of semiconductor, call it silicon, and we have a mask here. So light is coming in, but it's only hitting half of the wafer because it's being blocked in the other half. You can call this a mask. Basically just blocking the light. All right, so obviously in this type of problem, you're going to generate carriers in this region. So if just below this we were to draw the concentration profile, I'm going to put the x-axis, the y-axis right in the middle here. So let's call this x equals 0. This is x. So that's the position. And on the y-axis we can draw sigma n. So obviously we're going to have a high carrier concentration here, and we're going to have a lower carrier concentration here. Now the question is what happens in the middle here, this part here. We'll get to that in a second, but let's first understand physically what's happening in the material. So we've generated a bunch of electrons in this region of the material. We also generate holes. They come in pairs. Now there's excess electrons and holes on the left side compared to the right side, so the electrons, all the holes will diffuse from high concentration to low concentration, and so will the electrons. So the electrons will do the same. You get the idea, right? This is becoming messy. They all diffuse from left to right, light side to the dark side. The dark side of the force. So as this happens, when the electrons diffuse, what's going to happen to the electrons after a certain amount of time? They recombine, exactly. So we can denote, let me delete some of this stuff so it's clearer. So this electron will diffuse over to this side and it'll recombine. We just denote that with an X. The holes do the same thing. Okay, so there's diffusion and recombination happening in this problem. Now, I'm getting ahead of myself here. The reason I started drawing that diagram is to show you that the speed of diffusion is proportional to the concentration gradient, dN of x dx. Now, what we'll eventually find out is that this actually forms an exponential profile like this. Okay, so this will look something like, we call this sigma n 0. This will be a very similar equation. Sigma n, let's erase this. Sigma n of x, remember last time it was sigma n of t, now it's sigma n of x, is equal to sigma n 0 e to the negative x over L sub n. This here is called the diffusion length. The diffusion length is the average distance an electron or the electron diffuses before it recombines. Let me repeat that. It's the average distance an electron diffuses before it recombines. We'll come back to this in next class. But the point I want to make here is that getting back to the concentration gradients, the sharper this profile is showing sigma n of x. Okay. The sharper the concentration gradient is, meaning the steeper the slope, the more diffusion current you're going to get. So if we were from here, we can do Jn of x. Jn of x is equal to q times d sub n d dx, so the derivative of n of x. Q times dn d dx, derivative of e to the negative x over L sub n. What's the derivative of an exponential function? Another exponential function. So it's just q times dn negative 1 over L sub n multiplied by e to the negative x over L sub n. Right, so just by taking the derivative of the function, we can figure out the diffusion current. Using Fick's law. Now notice you have a negative here. Negative sign indicates that the current is right to left. It's going in the So the intuition here, the electrons are moving. When we're looking at the diffusion current due to electrons, electrons are diffusing from left to right. The current is opposite the movement of the electrons, right? So the current is going to be right to left. So Jn is going in this diagram. J sub n is going in this direction because the electrons are moving from left to right. All right, so simple example of Fick's law in when we talk about the diffusion due to holes. Same idea, except you have a negative sign here. Let's see why the negative sign happens. The holes move from high concentration to low concentration, and the current is in the same direction. So J sub p is in the same direction as the holes are moving. So that's the reason why you have this. That's the reason why you have a negative sign here. Constant D is the diffusion coefficient. D depends on temperature and to a lesser extent on the doping conditions. And basically, diffusion is driven by a concentration gradient. Okay. Drift currents are driven by electric fields. Diffusion currents are driven by concentration gradients. So at this point, we're going to start off with this next time. But we basically have summarized the 4 carrier processes now. And we even have relations for all of them. So electrons and holes can be generated through thermal, optical, or other means. And we have this equation which describes the generation and recombination rates at equilibrium. Drift, we talked about equations for drift currents for electrons and holes. Now we also have equations for diffusion currents for electrons and holes. And then recombination, the same relations that apply for generation, we can also apply those to a recombination as well. We also have that time-dependent equation that we just talked about earlier, describing the carrier concentrations versus time. So next time we'll combine the drift and diffusion equations to come up with a very general fundamental equation called the continuity equation. Okay, any questions for today? Okay, I will post the homeworks today, so please do get started on that. We'll have the quiz next Tuesday. And we're going to do one presentation today, so let's get going on that.